Welcome, ladies and gentlemen, to our lecture on conservation of momentum. So let's start by introducing the quantity momentum. Momentum, which we usually designate with little p, is an object's mass times its velocity. Now notice that unlike an object's energy, momentum is a vector. Okay? So when we add momentum, we have to use vector addition. We can't just add the magnitudes like we can with energy. So this means that we have to add components, right? Px equals m1 v1x plus m2 v2x plus etc., right? And then for the y component, m1 v1y plus m2 v2y plus etc. Okay? We have to use vector addition. We cannot write P equals m1 v1 plus m2 v2 plus etc. etc. Okay? Unless they just happen to both be pointing in the same direction. We have to make sure that we use this vector addition that we were using for things like forces when we are concerned with momentum. So where does this idea of momentum come from? Let's start to answer that by first looking at something called impulse. So notice that if we write Newton's second law, we can replace this A with dv dt, right? Because the acceleration is just the rate of change of velocity, okay? Then, if the mass of the object isn't changing, which is generally the case, right, we can write that the net force is the time rate of change of momentum. Now, if we have this net force over some period of time, delta t, that is impulse, okay? So when we have some net force times delta t, that's equal to impulse, which your book uses J, so I'll use J as well. Now, note that time is a scalar, but this net force is a vector, okay? So impulse, then, is also a vector. And remember that our sum, this sum f, for some fixed period of time, so if we took this equation up here, and instead of some infinitesimal time dt, we had some fixed period of time delta t, then this sum f is actually delta p over delta t, okay? The delta t's cancel, and we get this equation up here, which is our momentum impulse theorem. Now, much like our work energy theorem, if the net force isn't constant, we can look at an infinitesimal piece of time and keep adding up those little infinitesimal pieces of time, and we get an integral, okay? So then J is equal to sum of f dt, okay? In an integral like this. And then putting in this dp dt for this sum f, we see that what we end up with is an integral over over momentum, okay, the changing momentum. So going from this piece to this piece, we put in dp dt, right, and then it's dt, this integral. And these dt's kind of cancel. We're looking at the time rate of change of momentum, but then we're also integrating over time, okay? And so what we end up doing is we change our integral from time to momentum, and we integrate over the momentum, okay? Over the change in momentum, over whatever period of time we're concerned with. So we have this impulse momentum theorem, and we had the work energy theorem before. And notice that the impulse momentum theorem, so impulse equals, and I'm going to write this with the force, okay? We're going to write it this way. This impulse momentum theorem is a force applied over a time, right? And remember, the work energy theorem was a force applied over a distance, okay? Now, applying a force over a specific time gives us this impulse, okay? And applying a force over a specific distance gives us this work. The impulse changes the object's momentum, okay? So we end up with impulse is a change in momentum. And remember, when we were talking about work, we said that work was a change in the object's kinetic energy, right? So J, the impulse, is a change in the object's momentum, which is a vector, mv, and work is a change in the object's kinetic energy, which is a scalar, 1/2 mv squared. Okay? So remember that these are two completely different quantities. In fact, these are two completely different types of quantity, right? One is a vector and one is a scalar. So this brings us to conservation of momentum. Remember that we had conservation of energy as an immutable law of the universe. And we had the specialized case of conservation of mechanical energy for the types of systems that we're concerned with in this class, right? Conservation of momentum is another immutable law of the universe, okay? Conservation of momentum is always true. It's true for Newtonian mechanics, it's true in relativistic mechanics, it's always true. So conservation of momentum can actually be derived from the homogeneity of space, and that is that physics doesn't change from location to location in the universe. So if I had some system of objects interacting or something, and they're in some piece of space, if I took this whole system and translated it over to some other spot in space, it wouldn't change anything, okay? We call that the homogeneity of space under linear transformation. Now, based on just this simple principle, the fact that the physics won't change if I transport things in space like this, we can show that conservation of momentum must then be a property of the universe, okay? We're not going to do that in this class. It's pretty far past the tools that we have in this class. But it's amazing that the fact that I can displace a system from one piece of empty space to another without changing the way it works leads directly to momentum being conserved as a consequence of that property, okay? So what does conservation of momentum actually say? It says that if we have some system, okay, I'm just going to write system. So this is some system of physical objects interacting, okay? If we have some system with no net external force, okay, so there's no forces going into or out of our system like this, no external forces, or if those external forces, if the vector sum of the external forces equals 0, then the momentum of the system is constant, okay? So if we took this initial momentum and this final momentum, they would be equal. And that means that for all pieces in the system, I can do a vector sum, okay? So m1, v1 plus m2, v2 plus etc., okay? That equals P, let's say I, right? Or P final, whatever. In both cases, I can add up. Remember, this is a vector sum, okay? So I'm not actually just adding these. I would have to break them into components, add up the components, and then recalculate recalculate the velocity for the whole, okay? So all of the little pieces in the system, when I add up the momentum like this, I have some quantity, the total momentum of the system, and that will remain unchanged as long as the net external force on the system is 0. So note there that the key to conservation of momentum was that there were no external forces acting on my system, right? So I have some system of particles that are doing whatever they're doing in here. And as long as there's no external forces, momentum is conserved. This is a big part of the real power of this physics tool. There are a lot of situations where internal forces can become really complicated, but conservation of momentum doesn't care about that. It just cares about there not being external forces, okay? So I keep saying internal and external forces, but what do I mean by internal or external forces? An internal force has both sides of the interaction inside the system, okay? So remember Newton's third law, that forces are interactions, so they always have two sides. So imagine I have these two objects, and they're attracted to each other, okay? Maybe they're attracted by gravity or the electric force or whatever else, okay? So they're attracted to each other, and I'm considering this system in my problem, okay? This force has both directions, both sides of the interaction inside the system, okay? This is an internal force, okay? Now imagine I had some other object over here, and so this guy was attracted to him. Now in this case, both sides of the interaction are not inside the system, okay? The force of this guy being pulled this way is in the system, but the force of this guy being pulled this way is not in the system, okay? Because I'm only considering these two objects. This one is an external force. So let's consider a quick example. Let's consider me in free fall, okay? If I'm in free fall, if I consider the system to be just me, then this force of gravity, right, mg, that's an external force, right? If my system is just me, if I'm only considering me, then gravity is an external force, and we know that my momentum, P, equals mv, not ma, mv, we know that that's not going to stay the same, right? When I'm in free fall, my velocity is constantly increasing, right? Until I reach like a terminal velocity. If I'm in true free fall, where I'm only affected by the force of gravity, then my velocity will just always keep increasing, right? So we know that this momentum isn't conserved in that case, and it's because I have this external force, okay? On the other hand, if I'm considering myself in free fall, but then the system that I'm considering is me and the Earth, then the force of gravity between the Earth and me is contained within the system, right? I'm considering both objects in this interaction as part of my system. In that case, the total momentum, which would be m for me, well, we'll just use little m for me, okay? And my velocity of me, plus big M for the Earth, and the velocity of the Earth, that equals P for the system, okay? The momentum of the system. That, in that case, this momentum will be conserved. So the sum of these two momenta in the initial condition, say when I'm at the beginning of my free fall, and these two momenta at the end, okay, say the moment when I hit the earth, those two momenta will be the same. And this goes back to what we talked about before. Remember when we talked about Newton's third law, I told you that when you fall at the earth, technically you pull on the earth as well, right? The earth pulls on you and you pull on the earth. The thing is, this M is so enormous that barely anything happens to the earth, right? But in this equation for momentum, notice that it's directly proportional to both M and V, okay? So it can change my V a lot and change this V only very, very little to a almost negligible amount, to an actually, in an effective sense, a negligible amount, because this M is so big and this M is so small, okay? So a tiny change in VE gets multiplied by a great big number, and my big change in V me gets multiplied by a tiny number, okay? And in the end, this immutable law of the universe, conservation of momentum, holds for this system where I consider myself in the earth, because now when I consider both objects that are involved in this interaction, this force of gravity, this force is internal, okay? So Fg, internal. So now finally, with this conservation of momentum equation, note that I have this equation for conservation of momentum, and it's a vector equation, right? In particular, it's a vector equation with no dot products and no cross products, okay? So you can probably guess where I'm going at this point. When we have a vector equation with no dot products and no cross products, what does that mean? It means that our vector equation is actually a system of equations as long as we use orthogonal coordinate systems, okay? So for our classic kind of XY system, we have this vector equation. It's a vector equation with no dot products and no cross products. So it's actually a system of equations, which means it would be true if I wrote Pxi equals Px f. And then for the y component, it'd be Pyi equals Pyf. And again, this means that the motion in each coordinate direction is independent of the other one, okay? And this comes from our orthogonal coordinate system. So this would be 2D. Of course, if I had it 3D, it would be Pzi now equals Pzf. And this would be for Cartesian coordinates, right? This isn't coordinate dependent. It only requires that your coordinate system have orthogonal coordinates, which is, it's very, very rare that people even use coordinate systems that don't have orthogonal coordinate directions. So this is still true if we had spherical coordinates or cylindrical coordinates or something like that, okay? So what are the most common types of events where we use conservation of momentum? The answer to this is collisions, okay? And what do we mean when we say collisions in a physics class? We mean that objects have a relatively strong interaction for a relatively short amount of time, okay? This definition can be pretty broad. We'll commonly use this as macroscopic objects bumping into each other, but it can have a broader meaning than this. For example, it could mean particle interactions or gravity assists or things like that, okay? So we have two kinds of collisions. We have elastic collisions and inelastic collisions. So in both of these kinds of collisions, momentum is conserved, okay? So Pi equals Pf in both of these collisions. And that's what makes conservation of momentum so great, okay? Is that it's conserved in both of these cases. Elastic collisions come from interactions by only conservative forces. So you remember our conservation of mechanical energy had that work non-conservative term? That term equals 0 in an elastic collision. Okay? And that means that in an elastic collision, the kinetic energy of the system remains unchanged. Okay? So in an elastic collision, we have Ki equals Kf. Now note that the kinetic energy of the objects in the system usually will change, but the total kinetic energy in the system will be unchanged. Okay? And we'll see a really dramatic example of this in one of the lectures coming up. I'll solve a problem where theoretically my wife and I run at each other with two of those great big exercise balls so that we can have an elastic collision. And we'll see that her kinetic energy changes very dramatically, very violently, and but the total kinetic energy of the system, because it's an elastic collision, is unchanged. Okay? An inelastic collision is just the opposite. It's a collision where kinetic energy is not conserved. Okay? So Ki, in fact, is greater than Kf. We can go further than saying they're not equal. You always lose kinetic energy in an inelastic collision. Okay? So, in layman's terms, elastic collisions are very bouncy, and inelastic collisions are not as bouncy. Okay? What we're really saying, though, is in this case, this non-conservative work term is 0, and so we have conserved kinetic energy. And in this case, the work non-conservative is not 0. Okay? We convert some of the kinetic energy into other forms of internal energy, heat, sound, things like that. Okay? So we convert kinetic energy into other kinds of energy in inelastic collisions. So what kinds of things fall under these two categories? Elastic collisions of macroscopic objects require elastic objects. Okay? So the objects have to be able to bounce back to their original shape after they have some small deformation to have an elastic collision. Okay? So if we have two blocks with like springs on the front, okay, and they're flying at each other here like this, they'll bump into each other. They'll squish the springs by some amount, right? And then they'll fly back apart, and they'll be back in this shape, but with velocities like this after they bang into each other, right? That's an example of an elastic collision. The springs hit each other, they deform, and then as the objects move back apart, the springs bounce back to their normal shape. Okay? So they're shaped the same before and after the collision. Another example would be between two really hard objects, okay? Like two billiard balls. So when you're playing pool, the balls aren't getting dented and stuff like that, right? Because they're really, really hard. And really hard objects, like billiard balls or bowling balls and bowling pins and things like that, these really hard objects are elastic. They're just deformed very, very little by very, very large forces, okay? And any object, if we have enough force, will no longer rebound to its normal shape, right? So if you've ever pulled, you can stretch a spring and it'll bounce back to the way it was, right? But if you've ever taken a spring and just stretched it really, really far, if you stretch it far enough, it won't bounce back to the shape it had before you stretched it, right? If you have a billiard ball and you, say, shot it with a bullet or something, it explodes, right? It can't rebound back to its prior shape, okay? There's always some force for which an object can't rebound back to its normal shape, but really hard objects can sustain really big forces with really, really tiny deformations. So billiard balls are an example of this. They're elastic objects. It's just they're deformed so little that you don't even think about them being squished and then rebounding to their normal shape. Okay? When these objects collide, these really hard objects, they have elastic collisions. Okay? And that conserves kinetic energy. So on a billiard table, when you hit one ball with another, you have this collision between these two objects. Okay? And this collision conserves momentum, okay, and it conserves kinetic energy. So then what kind of things fall under the category of inelastic collisions? So in short, everything else, okay? If it's not an elastic collision, it's an inelastic collision. We said that elastic collisions conserve kinetic energy, so any collision that converts kinetic energy into some other kind of energy is inelastic. Okay? So what does that look like? One hallmark of inelastic collisions is that the objects are deformed. Okay? So if I have two cars, or roller skates, I don't know what I'm drawing. If I have two cars like this, and they bang into each other like this, then afterwards I might have one or both cars all kind of smashed up, right? Well, it absorbs energy to smash up the car, okay? And that energy is the kinetic energy that the cars have before they bang together, okay? It takes energy to manipulate all of the car's materials so that they're in a different shape. That energy comes from the kinetic energy of the cars, and so we have an inelastic collision. Okay. Now, an example you might be able to think of like this is a really simple one would be if I throw a baseball really hard in an old metal trash can. I leave a dent that persists after the collision, right? So I throw a baseball really hard at one of those old metal trash cans, and the trash can looks like this afterward. That's an inelastic collision, okay? Now, if I bounced it off really softly, I could have an elastic collision, right? The can can have small deformations and bounce back to the way it was, but if I hit it hard enough, I'll change to an inelastic collision, okay? In this collision of the baseball with the can, some of the kinetic energy is used to deform the can, right? So Ki greater than Kf, okay? Some of the kinetic energy that I gave the baseball is used to deform the can. Another example is when two objects stick together, okay? So imagine that I had two blocks, okay? And instead of springs on the front, they had Velcro on the front, okay? So then when they bump into each other, they stick together like this, okay? When objects stick together, some of the kinetic energy is removed by non-conservative forces acting to hold the two objects together. So in this case, again, Ki greater than Kf, okay? Or the way that we're generally describing it, they're not equal, okay? Notice this is a greater than, not a greater than or equal to. Strictly greater than, okay? They're not equal. So this leaves a question: do we truly see perfectly elastic collisions in the real world? Okay? The answer is not generally. When objects collide in the real world, there's always some kinetic energy converted into something else, okay? There might be some heat in the objects, okay? Even in the case when we had the springs, the blocks with the springs on the front. The truth is, when we squish those springs, they are heated by a tiny amount, okay? A tiny amount of energy goes into heating the springs. We always consider ideal springs, right, where this doesn't happen in this class, but the truth is, in the real world, that's not true, right? We might have some really tiny permanent deformations, okay? Or even in the case of the billiard balls, that seems like it's definitely got to be a truly elastic collision, right? But there's sound coming from it, right? If you've ever been in a bar that has a pool table, there's a very distinct sound when the two balls bang into each other, right? That sound is a pressure wave that radiates out from the point of contact, right? So when the two balls, let me draw them in contact here. When they hit each other, this point of contact, there's a pressure wave that radiates out. That's what sound is, okay? That pressure wave goes out and it vibrates your eardrum. It takes energy to create that pressure wave radiating out from the collision, okay? That energy comes from the kinetic energy of the billiard balls. Now, these types of things always exist in collisions in the real world, all right? At the bare minimum, you can think that any time we see a collision in the real world, we always have a sound with it, right? But the energy losses from these sources, they can be very, very small for many different types of collisions, all right? In our example of the billiard balls, the energy that creates that sound, very, very tiny in comparison to the energy of the system, okay? So we can approximate these systems as elastic without being wrong by very much at all, okay? In many cases, without being wrong by any amount that we can even detect with the kind of equipment that we have on hand, okay? So we can use the idea of an elastic collision in these real-world macroscopic cases without being wrong by enough to even be worried about it, okay? But the truth is, all of these macroscopic objects banging into each other, there's always a little bit of loss of energy. And at the most technical level, yes, they are all inelastic collisions, okay? So then let's think about a specific case. Let's consider two cars bumping into each other, okay? If the two cars bump into each other, and they both have these bumpers out here, okay? If the two cars bump into each other, and the bumper of neither car is deformed, okay? So they just kind of like slowly bounce into each other. The bumpers hit and they bounce back apart. And each of these bumpers isn't deformed. The car behind it isn't deformed, okay? Then we can approximate that as an elastic collision, okay? We'll call that an elastic collision. But if the two cars bump into each other and they kind of smash each other, then we'll call that an inelastic collision, okay? They permanently bend each other's shapes out of what they were before the collision, okay? So we can see that we can have either kind of collision between these same two objects depending on the forces involved, okay? Or depending on the momentum change that each object has, okay? And the different circumstances change the way the two collisions behave, okay? It changes which type we have and what they look like. The great thing about conservation of momentum is that it doesn't actually matter whether the collision is elastic or inelastic. In both cases, conservation of momentum is true, okay? The elastic versus inelastic designation is really only a consideration of whether or not kinetic energy is conserved. So let's look at a couple of collisions using conservation of momentum, okay? Let's consider two blocks moving right at each other and having an elastic collision. Okay? We can write the momentum beforehand. If we call this one M1 and say it has V1 beforehand, this one M2 and say it has V2 beforehand, then because this is one dimension, right, we just have x hat like this, I can write M1 V1 and then minus, because this V2 is in the minus x hat direction, M2 V2 equals M1 v1 final plus m2 v2 final. Okay? And now, because I said this was an elastic collision, I can also write 1/2 m1 v1 squared, the kinetic energy of the first block, right? Now this time plus, because when we square v2, then the sign dependence goes away, right? The kinetic energy isn't negative because of the direction the block is moving. It's still just positive. And that equals m1 v1 final squared plus 1/2 m2 v2 final squared, okay? And now, when I look at this, I now have two equations, right? This is one-dimensional, so I just get one equation for my vector equation here. But I have two equations, and if I knew m1 and v1 and m2 and v2, then I would know everything in this equation except v1 final and v2 final, okay? Then I have two equations and two unknowns, and I could solve for the velocity of each block, okay? And the velocity after the collision is going to be a function of the velocities before the collision, right? And the masses of the two objects, okay? And the behavior of the blocks is definitely going to depend on the masses of the two objects, right? Because the masses dictate their inertia. So if we want to take an extreme example, imagine that you threw, say, a baseball, M2, a baseball, at a moving train, okay? So you have like a bullet train or something, and you just toss the ball at the front of the train. They could have an elastic collision. V1 would change barely at all, right? The V1 might not even change to any detectable level. V2 changes dramatically, right? So the final velocities are going to depend heavily on the momentum of each, which of course is going to be proportional to both the mass and the velocity, okay? So you can have one object's momentum dominate the system because it's very big, like my baseball and train example, or because it's very fast, okay? In either case, you could have one object's momentum kind of dominate the whole momentum of the system, okay, and be changed very little. Now, you could also have where the masses are very similar and the velocities are very similar, okay? For example, a couple of billiard balls or something like that. If you, say, rolled two billiard balls at the same speed right at each other, then what you'd have is that their changes in their momentum would be the same, right? Now, the momentum of the system, both balls together, doesn't change, but the momentum of each ball does change, okay? So now, let's consider this same system, okay? But now let's say that when the two blocks collide, the final picture of this is that they stick together, okay? And then they have some shared velocity at the end, okay? So I can still write conservation of momentum, right? I could still write m1 v1 minus m2 v2. Again, the minus is just coming from my coordinate system, okay? We're really just adding up the momenta, but the momentum from this one here is going to be negative because it's moving in the negative direction, okay? That's all the minus sign is. And then that equals, and then the momentum at the end, okay? The momentum after the collision. In this case, I now have just one object, right? If these two are stuck together, they're really just one object with a mass m1 plus m2, right? And this velocity v final. Now in this case, I can't write kinetic energy, right? That's not conserved this time. I'm not sure what it is before and after, okay? I would have to find VF and then calculate the kinetic energy after to see how much kinetic energy was lost in them sticking together, okay? But I do have, in this case, it's one-dimensional again, right? So I still just have one equation for my conservation of momentum. But now, if I know M1 and V1 before the collision, and I know M2 and V2 before the collision, in this case, I just have one unknown because they stuck together. I'd have just this final velocity that's not known in my equation, okay? And again, I have one equation, one unknown, so I can do algebra and solve for this. In fact, the algebra is very easy, right? You can already see what VF must be, okay? So now, to go back to our discussion of elastic and inelastic collisions in the real world and conservation of momentum in the real world. Remember that we said that our system has to have a net external force. A net external force equal to 0 for conservation of momentum. Okay? Now, much like the elastic and inelastic collision thing, in the real world, it's very rare that the external forces are actually completely 0, right? But also, just like the inelastic and elastic collision thing, oftentimes the external forces are so small that it doesn't change the problem in any material way to just consider them to be 0, okay? So, if you had two cars bumping into each other and skidding somewhere, the net external force during the collision is so small in comparison to the forces involved in the collision that we can generally ignore them, okay? Now we know that if the cars are skidding, they'll skid to a stop without skidding very far, but for that instant in time where they're hitting each other, those external forces aren't very big, and we can often ignore them for that moment, and that moment is what we really care about with conservation of momentum, okay? The velocity right before they collide and the velocity right after. And then if we have that velocity right after they collide, we could use something like the work energy theorem or Newton's second laws to calculate maybe how far they would skid before they stopped, okay? So this net external force thing, in many of the problems that we'll look at, maybe the net external force isn't actually completely 0, but it's close enough that we can approximate it as that and still be okay. All right? So now let's use our new tool of conservation of momentum to do a little bit of light rocket science, okay? We know that we use rockets for space travel, but if I have a rocket out in space, okay, or maybe a Crayola crayon, whatever I've drawn here. If I have a rocket out in space, how does a rocket work when there's nothing to push against, right? If I have the rocket on the launch pad, it pushes against the ground to fly, right? But then how can it work in space when there's nothing to push against? Newton's third law says forces are interactions, and there's nothing around to interact with in space, right? So how can the rocket propel itself? The answer is that the rocket doesn't push against the ground to fly when it's on Earth, okay? This is a misconception that people have, that the rocket pushes against the ground or air or something like that. This is not true. That's not how a rocket flies, okay? So we'll do away with that entirely, and then we'll look in space. It flies in space the same way that it flies on Earth, okay? And the answer to what does it push against is actually the exhaust of the rocket, okay? You always see these big flames coming out the back of a rocket, right? What is that? The engine propels the fuel of the rocket to some very high velocity, and that fuel is pushed out the back. As the fuel is pushed out the back, okay, the rocket and the fuel push on each other. There's an interaction, right? The engine is pushing the fuel out. That's a force. We know that forces are interactions from Newton's third law. So they push on each other. When that happens, the fuel is pushed backward and the rocket is pushed forward, okay? Now, there's a lot of internal forces and things going on in there. It's pretty hard to kind of write this out by Newton's second law and figure out exactly how the rocket is going to move. But, like we saw before, conservation of momentum doesn't care about that, right? So if I have the fuel coming out of the back of the rocket, and I have the rocket, and I consider that whole system, then momentum is conserved in that system, okay? That's how a rocket actually propels itself, by conservation of momentum, okay? By Newton's third law saying that the exhaust and the rocket push on each other with an equal magnitude of force, okay? So let's consider a rocket moving through space with some velocity v, okay? Then it has momentum mv. Now, the mass of the rocket is actually the mass of the rocket plus the mass of the fuel, right? It's the mass of this object, which is made up of both rocket and fuel. So then if the rocket expels fuel to move, in some tiny amount of time dt, we're going to use our little infinitesimals here. So for some infinitesimal little time dt, the mass of the rocket changes to m plus dm. Okay? Some infinitesimal change in the mass of the rocket. Now, we know that this dm is negative, right? But because I'm ultimately going to use this to make it a derivative, we're just going to write plus, okay? And the derivative in the end will come out negative. So then the fuel has a mass that's just the opposite of the change in the rocket's mass, right? So if the rocket's mass goes down a little bit, the fuel's mass, or the expelled fuel's mass, the exhaust mass, must go up, right? So we put a minus on this because it's the opposite of the change in the rocket's mass, okay? And the relative velocity of the fuel, which is now exhaust, is v minus vx. Exhaust. Okay? This v exhaust is the speed that the engine pushes the exhaust out the back, okay? So it pushes it out with some speed, but the exhaust, as it's sitting here with the rocket, is already moving with this v, right? With this guy. So it's moving with this speed, and I push it back with some speed v exhaust. Then if I was, say, outside the rocket looking at the system here, right, in a coordinate system that's not on either piece, in a separate coordinate system, what I would see is everything's moving together, and the fuel would be pushed out the back with a speed v minus v exhaust, okay? And then this would be multiplied by this minus dm, the mass of the exhausted fuel, to give the momentum of the exhaust, okay? And again, I'm not writing vector symbols on these because we're in one dimension, okay? The rocket is just flying straight. So I have pluses and minuses. I don't have vector symbols on top of my variables here. Okay? So the fuel is pushed out the back, and this is the momentum of the exhaust. Okay? For the rocket's mass is m plus dm after this little infinitesimal change in time, right? And then its velocity would be v, this velocity that it had at the beginning, plus dv, some infinitesimal change in the velocity, okay? So in an infinitesimal piece of time, we push out an infinitesimal piece of fuel, that becomes an infinitesimal mass of exhaust, and we have an infinitesimal change in our velocity, okay? Now, if you can understand that, our little piece of light rocket science here is going to be really easy from here on out, okay? So, I can always use conservation of momentum here because There's no external force on this, right? My system that I'm considering is both the exhaust and the rocket, so the only forces involved in this are internal. Okay? So my initial momentum, the rocket with all the fuel in it, is just mv, right? And then my final momentum is going to be this momentum of the exhaust. So we have this minus dm v minus v exhaust, okay, plus the momentum of the rocket, m plus dm v plus dv, okay? And this goes back to what I just told you about how the rocket moves. What this tells me is my rocket has some momentum, and the new momentum of the rocket goes up by the same amount that this momentum goes in the other direction. Okay, so I have more momentum going this way for the rocket because I've created momentum going back this way for the exhaust. Okay, so again, the way rockets work, they don't push on some external environment factor like the air or the earth or something like that. They work by conservation of momentum. So now, if I expand this equation, I would have minus dm times v plus dm times v exhaust plus mv plus m dv plus dmv plus dm dv, okay? And then if I look at these terms, you notice I have a dmv here that's negative, and I have a dmv here that's positive. So they cancel, okay? You notice I have mv here, and the other side of this equation is mv. So if I subtract it from the right side and subtract it from the left side, I end up with 0 on this side, okay? And this term is gone. And then I have dm v exhaust times m dv times this little guy out here, dm dv. And what I'm going to do with this dm dv guy is something that physicists do all the time that's a little bit hand-wavy, but when we're looking to predict things in the real world, this actually works really well. Okay, so it seems hand-wavy and it seems oversimplifying, but it actually works. Okay, so what I'm going to say is, remember that these are all infinitesimal little pieces. They're just the tiniest little changes in mass, okay, and velocity. And if I have just this infinitesimal little piece, and then I multiply it by another infinitesimal little piece, okay, then I have infinitesimal squared, okay? And infinitesimal squared is really, really tiny, right? In fact, it's so tiny that I'm just going to ignore that piece, okay? It's so tiny that it won't affect my system in any real material way. And then what we have is dm v exhaust plus m dv. Okay? So now I have this equation that came from conservation of momentum of the rocket and the exhaust, and I can write it like this. M dv equals minus v exhaust dm. Now remember that this was all happening in some infinitesimal piece of time. Okay? So if I divide my equation by that infinitesimal piece of time, I end up with dv dt here and minus v exhaust dm dt. Okay? But this side, m dv dt, that's just net force, right? That's the net force on the rocket. Remember, this dv is the change in the rocket's speed. And that's equal to the speed that the engine pushes the exhaust out times dm dt, the derivative of the change of mass with respect to time. Okay? So this is the force that the engine of the rocket is pushing on the rocket with. Or to be slightly more accurate, this is the force that the exhaust pushes on the rocket with. Okay? So let's write that up here. And remember, these are all vectors. I'm just dealing with a one-dimensional problem, right? So I'm not putting the little harpoon on top of the variables. Okay? So now let's look at our equation again. And what I'm going to do is I'm going to bring the m over to this side, okay? And I'm just going to put primes on all the variables. Now, the primes don't mean anything, okay? I'm just renaming the variables because I want to use this name again in the end, okay? And I'm going to perform, what I'm going to do is perform an integral. But so the primes are just a new name that's going to stand in for the variables, okay? The variables all still mean the same thing, but these little primes on them are just a new name so that I can do some math here, okay? So now, if I integrate both sides, say from v to v final, let's even say v naught, okay? So let's say the starting speed of the rocket is v naught to v final, and then I integrate these little changes of speed. Now what I'm doing is coming to some macroscopic time, right? I'm integrating this thing that's happening in a little infinitesimal piece of time, so I'm finding a macroscopic effect, okay? And that's minus VEX, okay? We're going to assume that the exhaust speed of the fuel is constant, which is a pretty good assumption, okay? Is m naught to m, okay? So this would be the initial mass of the rocket, and this is the mass at the end of some burn, right? At the end of some usage of fuel. And again, the integral is bringing us to a macroscopic change in the fuel, right? And then I have 1 over m prime dm prime. And I integrate over m, okay? Now, if I integrate this left side, it's just going to be VF minus V naught, right? And that's going to be delta V, right? Right from the very beginning of the class, we talked about delta some variable being final minus initial, right? We talked about it with displacement. Final position minus initial position was delta x, okay? This delta v is the same thing. It's the final velocity minus the initial velocity. So it's the change in velocity, okay? And that's going to equal minus the velocity of the exhaust, okay? And then the integral of 1 over m here is going to be the natural log of m, okay? That's just calculus. And then I plug in my variables here, and what I end up with is the natural log of m minus the natural log of m naught, okay? And then by properties of logs, this is minus v exhaust natural log, not h, natural log m over m naught, okay? And then finally, that leaves us with this equation, delta V equals V exhaust. And then I'm going to bring the minus sign inside the log and use another property of logs. Bringing the minus sign in will just flip this fraction. Okay? And I get this V exhaust natural log m naught over m. Okay? And this one is called, I've usually heard it just called the rocket equation. I'm not sure if it has a more proper name. It might, but I've generally just heard it called the rocket equation. Okay? So there we go. We managed to dust just the lightest little dusting of rocket science into our intro physics class here. And you'll hear people talk about delta V for rockets, okay? They'll often talk about doing what they call doing a burn, which is burning fuel to change a rocket's speed. And that changes its orbit. Okay, so you can modify a rocket's orbit around whatever it's orbiting by changing its speed. Okay, and they'll talk about the delta V that a rocket is capable of. Okay, and that's this equation. They're talking about this delta V. Okay, so note that in this equation, if I want a rocket to go really fast, the key is to make as much of the mass fuel as possible so that I can burn off most of the mass of the rocket. Okay? This m naught is the initial mass of the rocket, so that's the rocket with fuel, right? So I have my rocket here. Oh. I have my rocket here. And this is it with fuel in it, right? M naught. And then if I want the rocket to go really, really fast, the key is to make this number in here big, okay? The bigger I make this number, the bigger I can make the delta V of the rocket, okay? And to make that number big, I want this M to be as little of M naught as possible, okay? Does that make sense? So this M is going to be the rocket afterward. Now say with no fuel in it, okay? So I have all this mass in here, and that's just, in this rocket, empty space, okay? I'm just left with empty shell, and all of this is empty, okay? So then this is this M, and this one is M naught, and you can see if I have a whole bunch of fuel in here, I can burn away most of the mass of my rocket, and I can make this number inside the natural log big. Okay? And if I do that, I'm going to make delta V big. So if I want to build a fast rocket, the key is to have lots of fuel so that I can burn off all the fuel. Okay? Now, in practice, when I go to do this, I run into problems because at the beginning, when I first start burning fuel, if I have tons and tons of fuel, I make M naught really big. And so then the change from M naught to M is really small at the beginning when I only burned off, say, this much fuel. So I don't get a very big delta V on my rocket because I'm not changing the mass very much by burning fuel. Okay? This is something called the momentum problem. And this is a problem with trying to take rockets to really big speeds so that you can do something like go to a planet that's really, really far away, or go to even, say, another star. If you think about science fiction type of things, trying to go to another star, you run into a problem where you're like, oh, well, I'll just make most of my mass fuel. But then the problem is my rocket has really poor performance at the beginning of the fuel burn, right? And so what you'll sometimes see are the things like the booster rockets and things where I can have a rocket with a bunch of fuel, and I burn all that up to help it get going in the beginning, and then I actually drop off that piece of the rocket so that when I go to do my next burn, a higher percentage of that one is fuel because I'm not carrying around empty shells. Okay? So this equation for delta V that I've called the rocket equation, this is an equation that you may use in the future without derivation when it's appropriate. Okay? I'm giving you this equation to use prima facie if I ask you a question about rockets that this pertains to. Okay? So go ahead and write this down. Go ahead and use this one without derivation. This is a new basic physical principle that you know. We'll use conservation of momentum to consider many kinds of problems, most commonly collisions, but from time to time other things as well. And in future lectures, I'll do some more example problems using conservation of momentum. And then, of course, in your homework, you'll have ample chance to put this tool to use and get a really good handle on how this tool works.